All right, so we are going to discuss significant figures. And this is really just helping us identify the important digits in a measurement. This is going to help us later down the line when we are working with scientific notation, which is another important concept in science. So what are sig figs? Sig figs are the digits in a measurement that are either knowns or estimates. So for example, 130.56 centimeters has 5 significant figures. The knowns are 130.5 and the estimates are the 6. If you count all of those digits, you get 5 significant figures. So each of those digits is a significant figure. Digits that are unknowns are not significant. So unknowns are always zeros and they are usually used as placeholders. So if you look at the number 5,600,000 liters, there's only 2 significant figures in there. The 5 is a known, the 6 is an estimate, and the zeros are all just placeholders in there. Because the 6 is an estimate in here, we can't define those other numbers that are just zeros. So this would be the equivalent if we were talking in large terms. They made $5.6 million last year. Do you think they actually made exactly $5,600,000, or is that a rounded figure? So the 5.6 million is a way of abbreviating that. So what is significant in a measurement? All non-zero digits are significant. This means in the example of 4.23 milliliters, the 4, the 2, and the 3 are all counted as significant figures. Therefore, there are 3 significant figures in that one. Similarly, in 129.46 grams, all of those numbers are non-zero numbers, so they are all significant numbers. So there are 5 significant figures in that value. Zeros in between significant figures are also significant figures. This means that in 209 kilometers, the 2, the 0, and the 9 are significant. In this particular case, the 0 is only significant because it is contained between 2 non-zero numbers. Similarly, 40,098 has 1, 2, 3, 4, 5 significant figures. Both of these zeros are between 2 non-zero numbers, therefore they are also significant. The last digit after a decimal point is also significant. So in the example 9.0230 meters, that has 4 significant figures. The 9, the 2, the 3, and the 0 are all significant. In 23.3320 grams, the 2, the 3, the 3, the 3, the 2, and the 0 are all significant. Therefore, there are 6 significant figures in that value. Zeros used in scientific notation as coefficients are also significant. Scientific notation can be seen below in the example. This is where you have a value times 10 by some sort of exponent there. The numbers on the left side of the multiplication side are the coefficients. Therefore, 6.00 is the coefficient. All of those values are significant, so that is 3 significant figures. Similarly, 4.0 times 10 to the negative 4, that is 4. The 4 and the 0 are both significant in that value. Numbers that are not significant, zeros that are used as placeholders are never significant numbers. So zeros can be used as placeholders in decimals, and they can be used as placeholders in large numbers. So in the example 0.0002, the 0 on the right hand, because they come between the decimal place and the number, are counted as placeholders. So none of those are significant. There is only one significant figure in that example, and that is the number 2, because it is a non-zero number. Additionally, in 1,000 kilometers, the 1 is the only significant figure in there. There's only one significant figure in 1,000. All of the other zeros are considered placeholders between the significant figure and the decimal place. Zeros used to draw attention to decimal points are also not significant. So when we put a 0 in front of a decimal place, like 0.12 milliliters, that 0 is not a significant figure. We're just using that as a placeholder. There are only 2 significant figures in that number. Additionally, in 0.234 centimeters, there are only 3 significant figures. The 0 does not count. Rules for identifying a significant figure in a measurement. We are going to learn 5 rules. You guys are going to be asked on your assignments to identify which rules allowed you to determine how many significant figures were in the problems. So rule number 1, all digits, all non-zeros are significant. So all numbers aside from 0 are always significant. In measurement 1, 25 grams, there's 2 sig figs. In the next one, there are 4 sig figs. In the 47,689 kilometers, there are 5 significant figures. I miscounted. And in the following one, 972, there are 3 significant figures. Go ahead and try and practice on your own. If you guessed 6 significant figures for this one, you are correct. The 4, the 5, the 6, the 8, the 5, and the 7 are all significant figures. Rule number 2, zeros between significant figures are significant, or significant digits are significant. So in our first one, 4.09 centimeters, the 4, the 0, and the 9 are all significant. Therefore, there are 3 significant figures. In the following, there are 5. In the next one, there are 1, 2, 3, 4, 5, 6, 7 significant figures. And in the following one, there are 4. Take a second. How many sig figs in the following measurement? 902. If you guessed the answer as 3, that is correct. Good job. Again, these are significant because they are contained between 2 other significant figures. Rules to identifying significant figures in a measurement. Number 3, final zeros to the right of a decimal are significant. So in the case of 2.0 mLs, there are 2 significant figures. The 2 and the 0 are significant. In this case, again, the 0 is considered a significant figure because it is the final 0 to the right of a decimal. This one right here, the 2, the 9, the 3, the 0, and the 0 has 5. That's because the final 0 to the right of the decimal is significant. Because of that, we can incorporate the other rule that zeros between 2 significant figures are also significant, so that makes both of these zeros significant figures. The next one has 4. The 1, the 0, the 5, and the 0 are all significant. Again, the 0 sandwiched between the 1 and the 5 are automatically significant because of rule number 2. And this one at the end, the 0 at the end, is significant because of rule number 3. The last one is also 4, and again, it's because the final 0 is a significant figure based on rule number 3. In 49.90 meters, the answer is 4. Again, the 0 at the end is a final 0 to the right of the decimal place. Rules to identifying number 4. Zeros used in scientific notation are significant. So these are numbers that are to the left of the multiplication. These are our coefficients. So in the first coefficient, 2.0, there are 2 significant figures. We do not count any of this stuff over here as significant figures, simply because those are going to end up being placeholder zeros if we were to expand that from scientific notation into traditional notation. 3.04, there are 3 significant figures in that value. In 1.00, there are 3 significant figures in that value. And in 1.8, in 8.000 times 10 to the 23rd, there are 4 significant figures in that value. In the example, 6.010 times 10 to the 9, if you guessed 4 as that is the correct answer. Final rule number 5, zeros used as placeholders are not significant. So in the first one, the 2 is significant, the 1 is significant, and the 0 is not. There are 2 significant figures there. In this case, the 0 is considered a placeholder. In the second example, 0.002 centimeters, all zeros are considered placeholders in this one. The 0 to the left of the decimal place is not significant because it is a 0 just used to emphasize that we are using a decimal place there. And then the zeros between the decimal place and the 2 are considered placeholders. There's only one sig fig. In the next one, we have 0.030 meters. In that one, the 0 to the left of the decimal place is not significant. The 0 to the right in the 10th place is also not significant. That is considered a placeholder. The 3 is significant, and the 0 at the end of the decimal place of the number is significant. The reason that is significant, again, is because of rule number 3. Zeros at the all the way, the final 0 or the final number to the right of a decimal place is always significant. So the 2 is significant in that case. The final one, 1 million. Believe it or not, in 1 million, there is only one significant figure. That value is 1. All of the other zeros are considered placeholders. They are between the decimal place and the only significant figure in the value. If we were going to take this guess, out of 100 million, if you guessed the number 1, you are correct. 1 is the only significant figure in that value. To practice, 103 meters, that is 3 sig figs, and that is based off of rule number 2. The 0 is sandwiched between 2 sig figs. 100 grams, there is only 1 sig fig, and that is because of rule 5, that the zeros are placeholders. 6.02, there are 3 sig figs, and that's from rule number 4, saying that all coefficient values are significant. The next one, there are 4 sig figs, and that is based off of rule 3. Rule 3 states that the zeros all the way to the right of the final number to the right of a decimal place is always significant. And the final one, 173.673, is 6 sig figs based on rule number 1, that all non-zeros are significant. Again, a few more practice, 412. This is 3 sig figs based on rule 1. 10,000 cups, this is 1 sig fig based on rule 5. 0.001000 microbes, that is 4 sig figs, and that's based off of rule 3, and also rule 5. So rule 3 states that 0.00, those zeros are not significant because they are considered placeholders. However, once we have the number 1 in there in a thousandths place, all of the zeros to the right of that are significant because of rule number 3, saying that the final digit is significant. 5.00, again, 3 sig figs based on rule 3. We have 4 sig figs in this one based on rule 2 and rule 5. Rule 2 is that the 9 is significant. The 2 zeros after the 9 are also significant based on rule 2, that they are sandwiched between 2 sig figs. The other sig fig is the number 2. And then the 0 at the end is considered a placeholder, so it does not count. That makes it only 4. The next one is 3 based on rule 4. We then have 3 again based on rule 3 and rule 5. We have 1 sig fig based on rule 5, 3 sig figs based on rule 1, and we have 5 sig figs based on rule 2 in the final. So what are the rules to show a zero is significant? Some zeros can be significant if the scientist who measured them was certain that the zero was a measurement or an estimate. So if we can confirm that the zero is either a known or an estimate, then it is considered a significant figure. If it is an unknown, it becomes not significant. So we can show that zero is significant in one of three ways. If we needed to notate that 200 coins, that the two zeros were significant, we could place a line over top of the significant zero. We could display the answer in scientific notation. This second one is the traditional value in science. And then we could also place a decimal after the zero. All right, the second one is the one that we are going to use the most frequently as we make our way through the math program. Notice we wanted 200 coins. So the way to change that into scientific notation, as we will learn later this week, is it becomes 2.00 times 10 to the 2 coins. Having those two zeros there indicates that those are significant places, and that those are not just placeholder zeros. So 4,000 kilometers, 1 sig fig. 4,000 cups, 4 sig figs, because it has the period at the end. 6.0 times 10 to the 3 microbes, 2 sig figs. 50,000 feet, 1 sig fig, because it does not have the period at the end, right? There's nothing to tell us that it's supposed to be that. 70,000 10 ants, 4 sig figs. Again, 1, 2, 3, 4. There's no period at the end here telling us that this zero should be counted as a significant figure, so we don't. However, the following example, 70,010 period or decimal place, has a 5 sig figs. 560 has 3 sig figs because that line is placed over top. That tells us that the zero is significant. 560 glasses only has 2 sig figs because there is no line over the zero saying it's significant. 0.000045 pens, that is only 2 sig figs. And 0.000450 has 3 sig figs. That zero at the end, remember, is significant. Significant figures in addition and subtraction. So when we manipulate numbers using addition, subtraction, multiplication, and division, it determines how many significant figures we can carry. For example, if we're adding a number that is 10 plus 10.00004, how many sig figs do we carry our answer out to? There are rules for these. So when adding or subtracting, do your calculation first, then round your answer to the same precision as the least precise measurement in your work. So usually this is the least number of decimal places. For example, 2.3 centimeters and plus 1.2356 centimeters equals 3.5356 centimeters. We round that to 3.5. So we use sig figs to round it to the appropriate level. Again, we know how to do this because we go to the least precise measurement. The least precise, again, is typically the one with the least number of decimal places. 2.3 is less accurate than this one right here. It's less precise, not accurate, I'm sorry. So we must round there. So when we get this, we get 3.5. We look, the 3 does not round the 5 up at all, so we're left with 3.5. So we would do it precise to the 2.3, or to the 10th place, and the other one is precise to the 10,000th place. We leave our unrounded answer, and then we correct the answer to a rounded, to the least precise measurement. When we multiply and divide, we again do the calculation first, then we round the answer to the same number of sig figs as the least number of sig figs in the measurement in the work. So here's our example, 5.7 centimeters times 456.345 centimeters equals 2,601.1665 centimeters. We round that to 2,600 centimeters. So the reason why is because our least number of sig figs in the example was 2. So that means in our answer, we're only going to be able to use 2 sig figs. So we multiplied a 2 sig fig number by a 6 sig fig number. We got our unrounded answer, and then we correctly rounded this to 2 significant figures. Okay, so that is the appropriate way to provide significant figures here. Now, please don't go to your math teachers and do this unless you're specifically learning about sig figs, because they might not accept your values here. That's something you would need to discuss with them. So using sig figs when making calculations, we are going to practice our rounding. So 10.91 rounded is 10.9. 15.67 rounded is 15.7. 14.35 is 14.4. 3.21 is 3.2. 8.67 is 8.7. And 7.33 is 7.3. So the rule is, if the final number, or the number that you're using as the determination of rounding, in this case it is our final number at the end, if it's between 0 and, well, if it's between 1 and 4, we round down, so the number remains the same. However, if it is between 5 and 9, the number rounds up, so this would have changed from a 6 to a 7. Again, if we're going to practice our rule for addition and subtraction, you guys go ahead and pause and try this on your own, and then play when you're ready. So 43.6 plus 41.007, we get 1 decimal place and 3 decimal places for those. 1 decimal place is our least precise, so we're going to end up rounding to that. So our answer needs to be in 1 decimal place. So we calculate our full answer, and then we round to the appropriate number of decimal places. Again, it's the same rule for subtraction. So if we're going to try this again, we have 6 decimal places in the first value, 4 decimal places in the second value. 4 decimal places is our least precise number. So our answer will end up being rounded to 4 decimal places. So we have our full answer there, our calculated answer, and then our rounded answer below. Notice that we rounded the 3 up from a 3 to a 4 because of that 5 after. Again, practice. 2 decimal places, 5 decimal places. 2 is the least, so it's going to be 2 in the answer. We get our calculated answer, and then our rounded answer, 2 decimal places. All right, got 1 decimal place and 1 decimal place. Our answer is going to be in 1 decimal place. We can leave it, it does not need to be rounded. All right, another one, 1 decimal place and 0 decimal places. 0 is less than 1, so our answer is going to end up being in 0. We take our calculated value and we round it. We are not allowed to have a decimal place in that one. Okay, we would round that down to 9 kilometers. Again, here we go. 3 decimal places, 1 decimal place, 1 is less. 1 decimal place is in our answer. There's our calculated value, and we have 1 decimal place after. So least precise and least precise place. All right. Multiplying and dividing using sig figs. How do I use sig figs when making my calculations? So number one, how many sig figs are in number one? There are 3 sig figs in number one. There are only 2 sig figs in number two. So the number with the least number of sig figs is number one or number two. So number 2 minus 2. We have 4 sig figs, then we have 3 sig figs, and then 2. Sorry, I didn't mean to say minus 2 in the last one. The number with the least sig figs in that one is number 2, which is 3. So this one has 3 sig figs, this one has 2 sig figs. So the second value, number 2 right here, 4.2, would be what we used as our value, and that would be 2 sig figs. 2 meters, 2.0 meters has 2 sig figs. 3 meters has 1 sig fig. And in that one, we're also going to take the second number, which only has 1 significant figure. 16.000 kilometers has 5 sig figs. The next value has 4 sig figs. 4 is less, so we would use number 2. Okay, so now that we know these 2 simple skills, let's take a look at the rule for adding and subtracting measurements using significant figures. When multiplying or dividing measurements, round off the answer so it has the same number of sig figs as the measurement having the least number of sig figs. So for example, when we're measuring, rule for multiplication or division, we have 6.0 centimeters multiplied by 4.56 centimeters. The first one, we have 2 significant figures. The second one, we have 3 significant figures. So our answer is going to have 2 significant figures only. If we multiply those 2 numbers together, we're going to end up with a number. This has 4 significant figures. It's too many. We need to round it so that it only has 2 significant figures in the answer. So the answer is 27. Again, if we can apply the same rule to division. We have 5 sig figs in our first value, 3 sig figs in our second. 3 is smaller, so we're going to use that in our answer. Our calculated value has too many significant figures, so we need to round that so that we only have 3 significant figures. The 3 is rounded up by the 5 behind it, so we end up with 9.14 for that one. Again, multiplication, we've got 3 sig figs in our first, 2 sig figs in our second. 2 is smaller, so those 2 sig figs are going to end up being in our answer. We have too many significant figures in our calculated answer, so we need to round it to 2. The appropriate answer for that one would be 31. Again, we've rounded it to only include 2 significant figures in the answer. Here we go, 8.47 has 3 significant figures, 4.2 has 2 significant figures. That is smaller. We get 2 sig figs in the answer. Our calculated value has many significant figures, so we round that to include only 2. All right, this is one of those cases, if you guys were wondering in the earlier part how we were going to end up with knowing if there's supposed to be 1 0 or 2 zeros or 7 zeros after the decimal place. This is one of the ways. This, along with the calibrating your instruments and knowing which values are knowns versus unknowns, are how we determine those 0 values at the end and what counts. All right, rule for multiplication or division, 16.000, okay, has 5 sig figs. The next one has 4 sig figs. That is smaller. We multiply those together. We get a very number with a lot of significant figures in there, but we need to round that down to just 4 sig figs. So there's our answer right there. 3.001 multiplied by 5.20, we get 4 sig figs for the first value, 3 for the second. 3 sig figs is smaller. So it's in our answer, our calculated value, and our rounded value. Again, we've got 2.0 divided by 3. So we have 2 sig figs, 1 sig fig. One is smaller, so that's going to be our rounded answer. Our value is 0.6667, and from that we're going to end up with 0.7. So things we need to remember. Zeros used as placeholders are not significant. In addition and subtraction, we round to the least precise. In multiplication and division, we round to the least number of sig figs. And we don't round ever until we have finished all of our calculations. If we round early or we round too soon, we mess up we decrease the precision and accuracy of our answer. So if we measured 8,000 liters and we were sure of the 8 and the first 0, we estimated the second 0, and the last 0 is an unknown. How could you show 8,000 liters having 3 significant figures? Place a line over the 0. Use scientific notation, which is the one that you guys are going to actually do. So learn this one, 8.00 times 10 to the 6. And that wouldn't be 10 to the 6. Actually, that would not be 10 to the 6. That would be 10 to the 3. That's a mistake in the answer. If the 0 is in the ones place, you can place a decimal after the 0. So that has 3 sig figs. However, this is not saying that 800 liters is the same as 8,000 liters. So I don't want you guys to get confused on that one. Really, again, this one is the one, number 2 is the one you guys should be using, and that 6 right there should not be a 6, that should be a 3 if we were also equating that to 8,000. All right, what I want you guys to do is go ahead and do the practice in your homework, and we are going to go over these answers tomorrow after you've submitted them.